So let's now talk about exponential functions. So an exponential function, if a is a positive real number different than 1, then we say that f is a exponential function if it looks like a to the x, right? Some number to the x, where a, that number is the base, and then x is called the exponent. So if a is bigger than 1, because remember it has to be something, a positive number different than 1, so if it's bigger than 1, we call this the exponential growth formula. If it's between 0 and 1, we call it exponential decay. And we can actually see that from our graph. So speaking of graph, for any logarithmic function, right, we have 3 points on the graph. So if we plug in 0 into this graph, so hopefully we can remember some of our logarithmic functions, or sorry, not logarithmic, exponential rules, right? If you have anything raised to the 0 power, you should just get 1. So no matter what a is, 0, 1 will always be on that graph. What happens if we plug in 1? So a to the first is just a. So whatever a is, 1a will be on our graph. And then let's look at -1. So if we have a to the -1, we see that that's just 1 over a. 1 over a. Also, this is just when a is bigger than 1. So there's lots of ways of doing this. You might have heard something else, but this is the way I like to talk about it and I like to think about it. So make sure that a is always bigger than 1. And if that's the case, then this is what our graph will look like. So we have 0, 1 on our graph. We have 1a on our graph. So 0, 1, 1a. And then we have -1, 1 over a, which will be less than 1, right? So if you notice, this is what our graph looks like. So this is why, if a is bigger than 1, it's called the exponential growth formula. Because if you can see, it's growing, right? So the domain, all the x values, we see that it goes from -infinity to +infinity. The range. So if you have a number raised to a power, right? So if we had 2 raised to a power, how could we make that equal a negative number? Well, if you plug positive numbers in, you're going to get a positive. If you plug in 0, you still get a positive. If you plug in negative numbers, you still get a positive, right? Because that'd be 1 over 2 if it was -1, for instance. So there's no way to get a negative number. There's not even a way to get 0, right? It's always positive. Which means that we actually have an asymptote. Right? The asymptote is going to be at y equals 0. It's that whole line. It never goes past 0. It can never even touch 0. Ooh. Here we go. So the range, it goes from 0 to infinity, not including 0, right? Well, that's going to be annoying. There we go. All right. So let's look at some examples. So let's sketch the following graphs. So y equals 3 to the x. So since it's 3 to the x, right, we see that once again, 0, 1 is going to be on the graph. 1, 3 is going to be on the graph. And then -1, 1/3 will be on the graph. I guess we can write it a little better. So it's just going to look like this, right? Like the regular graph. All right. What about y equals 3/2? Well, notice 3/2 is greater than 1, so the sketch is also going to just be the same thing, right? It's just going to go up. What about y equals 1/2? Okay, so now this is not greater than 1, right? This is actually less than 1. So we got to do some maneuvering, right? So remember, you can always make this greater than 1 if you raise it to the negative first, right? Or you do a -1. So notice that's the same as 2 raised to the -1, right? Because the negative means you flip it. So it goes from 2/1 to 1/2, and it's raised to the first power. So 1/2 is the same as 2 to the negative first. So then that means that that's y equals 2 raised to the negative first raised to the x. And we have an exponent raised to an exponent. You're just going to multiply. So that's to the -x. All right. So we know that 2 to the x is going to look like this. So let's remember our transformations. What happens when you have a negative on the x? So if you have a negative on the x, that is a reflection about the y-axis. Remember, transformations are really important. So if you need to go back to those transformation sections, go for it. So we see that it's going to look like this, right? It's a reflection across the x-axis. Now this, if you noticed, right, our original one it's between 0 and 1, right? So this is why it is called the exponential decay, because anything between 0 and 1 is going to go down. All right. So if we have 3 to the x minus 2, we already said, right, 3 to the x is just going to look regular, an exponential growth. So what happens if you subtract 2 to the x? So it's going to be a horizontal shift. Remember, you can set that equal to 0. See that it's positive 2, so it's going to the right 2 places. So this is what our graph will look like, right? Just shifts over to the right 2 places. All right, so let's have e to the x minus 2, or sorry, 3 to the x minus 2. So again, 3 to the x, that's a normal graph. If we're just doing a sketch and we want to subtract 2, transformation says that's going down 2 values. Right. So there we go. Where the asymptote now is going to be at y equals -2. All right, let's look at this. So find the exponential function of the form f equals b times a to the x that has the y-intercept at 5 and the point that it passes through. So the way to do this problem is first you want to find b, then you want to find a. First you want to find b, then you want to find a. So the first point we want to do, so first let's look at if we just plugged in the point, right? So if we have this point and we plug it in, it's 5/16 equals BA squared. That doesn't help us, right? We still have 2 variables. So plugging in this point right now is not going to help us. So let's try plugging in the y-intercept. So the y-intercept, what value, what point is that? What coordinate point are we at? 0, 5. So we see that we would get 5 equals b times a to the 0. Well, what's a to the 0? We said anything to the 0th power is just 1. So that's 5 equals b times 1. So b is 5. All right, so we've eliminated the first variable. So we know that f of x equals 5 times a to the x. And notice, right, there's no parentheses. So we would assume that a is the only thing being raised to the x, and this is being multiplied. So now we can plug in our point, right? Because now we have one variable. So 5/16 equals 5 times a squared. So if we divide 5 to both sides, we see it's 1 over 16 equals 1a squared. If we take the square root of both sides, we see that a is plus or minus 1/4, right? The square root of 1 over the square root of 16, which is just 1/4. And don't forget the plus or minus. However, what did we say about a? A, regardless, always has to be greater than 0 and different than 1. So we know that it's going to be positive 1/4. So we plug it back into our equation. F of x equals 5 times 1/4 to the x. This is how we would write it. Now, can we simplify that to 5/4 to the x? No, we cannot, right? Remember, PEMDAS. Exponents happens before multiplication and division. So you can't multiply and then do the exponent. You do the exponent first and then multiply. So that is as simplified as we can go. We cannot multiply. All right, let's do another one. So here's a little difference, right? We have a plus c scenario. So it gives us a horizontal asymptote, a y-intercept, and a point. All right, so let's look at this horizontal asymptote. So if we go back to example number 1, right? And we looked at all these graphs. So notice, right, our asymptote, it should always be at y equals 0, right? So a regular asymptote should be at y equals 0. We already talked about that. All right, so what happens if you have a negative in the x? What happens to the asymptote? Nothing. It's still at y equals 0, right? What happens if you subtract or add a number to the x? The asymptote is still at y equals 0. So where was the only place where we had an asymptote that wasn't at y equals 0? Well, if you notice, it's when we added or subtracted to the outside. That changed our asymptote. Which means, right, that our asymptote can only be changed if you add something to the outside, right? Which means that c has to be 72. So we get f of x equals b, a to the negative x, plus 72. And now we basically just do the same thing, right? The y-intercept is going to be the point 0, 425. So 425 equals b times a to the negative 0 plus 72. Of course, negative 0, positive 0, that's all the same thing, right? So this just goes to 1. So 425 equals b plus 72, which means that b equals 353. So plugging that back into our equation, so far now we have f of x equals 353, a to the negative x, plus 72. So now we've got to plug our last point in. So notice we're using every single value in here. So 248.5 equals 353, a the negative first, plus 72. So if we subtract, we get 176.5 equals 353, a to the negative first. So negative exponents always suck, so let's get rid of them. So we can get rid of this negative exponent by putting it on the bottom, right? So 176.5 equals 353 over a to the first, which is just a. So if we put this over 1, we see now we can just cross multiply, right? So we get 176.5 a equals 353. So if we divide both sides by 176.5, we actually see that a is just 2. So plugging that back into our final equation, we get f of x is 353 times 2 to the negative x plus 72. It doesn't really matter if you put the negative x inside or outside the parentheses, right? As long as we know it's clear, right? That's as simplified as we can go. Yes, you could also write it as 353 times 2 to the negative x plus 72. That's also okay. Just make sure that you do not include the 353. Good. Let's try one more. Hopefully between all of these we'll get it. So if you want to go ahead and pause the video, see if you can get it on your own, and then fast forward, see if I get the same answer. That might be a good way to, like I said, do these videos. All right. So once again, we see that the horizontal asymptote is y equals -2. That only happens by adding or subtracting, right? So we see f of x is b a to the negative x minus 2. Our point is 0, 16. So 0 is the thing that's going to cancel out the a. So we got 16 equals b a to the negative 0 minus 2. We see this just goes to 1. So 16 is b minus 2. So b is 18. If we plug it back into the equation, we get f of x equals 18 a to the negative x minus 2. Now we got an x-intercept, which means that we have 2, 0. So 0 equals 18 a to the negative 2 minus 2. So we can add 2 to both sides. I mean, right now, if we want, we could divide by the 18. So we get 1 over 9 equals equals a negative 2. Hopefully typically my 9s and a's look the same, so trying to write them a little different. All right, negative exponents suck. So to get rid of it, we just switch it, right? Put it in the denominator. So we get 1 over 9 equals 1 over a squared. We can cross multiply. So we get a squared equals 9, which means a is plus or minus 3. But since a is being raised to an exponent, right, we know it has to be positive 3. So, plugging it back into our equation, we see it's f of x equals 18 times 3 to the negative x minus 2. All right, so we talked about graphs. We talked about if we have a graph, how can we find our formula? We talked about if we have the formula, how can we do the graph? So let's talk about some algebra stuff. So just a quick reminder of the law of exponents. So we've already talked about some of these. So if you have a power times a power, and they have the same base, right? Then we can just add those exponents. If you have a power raised to a power, you multiply the exponents. If you have a power divided by a power and it's the same base, we can subtract the exponents. And actually, the way we can do it is we can either put it on the top where it's m minus n, or we can put it on the bottom where it would be n minus m. And basically, the easiest way to do this is whichever number is bigger, do it that way. That's typically how I do it. If m is bigger, I put it on top and subtract to get a positive exponent. If n is bigger, I put it on the bottom and subtract, so that way, again, you get a positive exponent. We already said that a to the first is just a, and that a to the 0 is 1. All right, last thing, and then we can do some problems. So an exponential function, as we said, is given by f of x equals a to the x. And regardless if it's greater than 1, remember if it's greater than 1, it's going to look like this. It's the exponential growth. If it's between 0 and 1, it's going to be the exponential decay. But either way, notice the graph is 1 to 1. Which means that these are satisfied. So the first one doesn't really matter. The second one's the one that matters. So if it's 1 to 1, remember what that says is that if you have, we'll say f of x1 and f of x2, right? If you have this, right? So essentially it would be if it's f of a equals f of b, then that proves that a equals b, right? But since we already have an a, let's just do f of, we have f of x1 and f of x2, that would prove that x1 equals x2, right? And what is f of x1 and f of x2? Well, that would be a to the x1 equals a to the x2. So if a to the x1 equals a to the x2, we can just say the exponents are equal. So if you have a base raised to a power equals the same base raised to a power, you can just get rid of the bases, let the powers equal the same thing. All right. And I'll just go right into this. All right, so let's start solving some equations. So we have a power, or a base raised to a power, the same base raised to a power, so we can just get rid of those bases. So 3x equals 2x plus 5. So then subtract, you get x equals 5. So that's it, we're done. All right. So we have a base raised to a power and a different base raised to a power. Okay, so we're going to try to get a base raised to a power equals the same base raised to a different power. So what do we know about 9? Well, 9 is the same as 3 times 3, right? Which would be 3 raised to the second power. So we can rewrite our equation as 3 squared raised to the 2x minus 5. What about 27? So 27 is 9 times 3, right? Which is 3 times 3 times 3. So that's just 3 cubed. So we could rewrite the left part of the equation as 3 cubed raised to the x minus 1. So don't quite have a base because this base is 3 to the third and this base is 3 squared, but we can use our law of exponents, right? Specifically law number 2. We have a power raised to a power, so that's 3 to the 3 times x minus 1 equals 3 to the 2 times 2x minus 5. And now we have a base to a power and the same base to a power, so we can get rid of those bases. So 3 to the times x minus 1 equals 2 times 2x minus 5. All right. Distribute 3x minus 3, 4x minus 10. We can move the x's to this side to get x, move the 10 to the other side to get 7. So x is 7. All right, next, we got all this and stuff. So there is more than one exponent on both sides, so let's just break it up. So 4 to the x. So we know 4 is 2 squared, right? So we can write 4 as 2 squared to the x. 1/2. How can we have that as 2 to some power? Because typically, I mean, it's looking like 2 is going to be the base we want, right? So we should see that that's 2 to the negative first, right? So we get 2 to the negative first to 3 minus 2x. 8. All right, we can break up 8 into 4 and 2, 2 and 2. So 8 is 2 cubed. So we can just write that as 2 cubed times, and then 2 to the x squared. All right, so now we just got to have, again, one base raised to a power, one base raised to a power. We don't have that yet. So power raised to a power, we just multiply the powers. Power raised to a power, we can multiply the powers. And then power raised to a power, we can multiply the powers. All right, we still don't have a power equals a power, right? We have multiple bases. So now we got to combine these, right? So remember, if you have a base raised to a power times a power with the same base, you just add the exponents. So that's 2 to the 2x minus 3 plus 2x equals 2 to the 3 plus 2x, right? We're just adding the powers. And now we have a base and the same base, so we can get rid of the bases. So 2x minus 3 plus 2x equals 3 plus 2x. So we see that's 2x equals 6. So x is 3. All right. 2 more word problems and then we are done with this section. So a drug is eliminated from the body through urine. Suppose that for an initial dose of 10 milligrams, the amount in the body temperature is this after T hours. So estimate the amount of the drug in the body 8 hours after the initial dose. So we're going to plug in 8 for T, right? So A of 8 is 10 times 0.8 to the 8, which is about 1.68. And what did we say the dose was? Milligrams. So you still got about 1.68 milligrams of the dose. Part B. What percentage of the drug is still left in the body each hour? Sorry, what percentage of the drug still... That's not worded well. Still... Okay. What percentage of the body still... Or sorry, of the drug still in the body is eliminated each hour? Okay, there we go. There we go. Okay. So... right now, what we can see is that when T... equals 0, right? What do we get? At 0 amount of hours, how much of the drug is in the body? So the initial dose is 10 milligrams, so we know the initial dose, right? The amount in the body is 10. So each hour, well, let's just see. So at 1 hour, how much is in there? So you can see T equals... Or sorry, A of 1 is 10 times 0.8 raised to the first, which is 8 in the body. So how much was eliminated? So we see that 2 milligrams was eliminated from the body. Excuse me. So what percentage was eliminated? We see 2 was eliminated out of 10 milligrams, which is 20%. So 20% was eliminated. And that's it. Another way that you can see that, right? This 0.8 represents 80% left in the body, right? Which would mean 20% would be eliminated from the body. So either way you want to think about it. Last problem. So the half-life of a radioactive plutonium is 24,000 years. So half-life means that half of the amount of this plutonium is left 24,000 years later, right? So if you have 1 milligram of a substance after 24,000 years, you now have 1/2, right? If you had 1,000, now you have 50. That's what half-life means of the plutonium. So if the initial amount is F of 0, then the quantity remaining is all of this. So let's find K. So we do know what half-life means, right? It means that you have half of the amount. So what could your initial amount be? We can just guess. It doesn't matter. So let's just say that the initial amount is 100. So we have 100 milligrams, which means that after 24,000 years, what's going to be our amount? It'll be 50, right? It halved it. And you can use any number here, right? So instead of that, we could have used, we could have used 2 milligrams and 1 milligram. We could have also used 10 milligrams and 5 milligrams. Well, I'll show you, right? No matter what we use, we end up with the same result. So let's plug that in. So we get 50 milligrams equals 100 times 2 raised to the k times 2400. So remember, you need a power. A base to a power equals a base to the same power. A base to a power equals a base to the same power. Now we have something times a base, so we need to get rid of that something, right? So we can divide this 100 to the other side. So we end up with 1/2 equals 2 to the 24,000k. Right? If we divide 100 to both sides. Now notice, if we use a different number, if we use the 2 and the 1, right? 1 equals 2 times 2 to the k times 24,000. Well, we need to get rid of this 2 to the other side, so we would end up with 1/2 equals 2 to the 24,000k. Oh, same thing. If we use 10 and 5, 5 equals 10 times 2 to the 24,000k. Divide by 10, 1/2. Oh, same thing. Right? So it doesn't matter what we use. We can use anything as long as we use the idea of a half-life, right? You start with something, you end up with half of it by the end of it. All right, so we need a base to a power equals the same base to a power. So how can we turn 1/2 into 2 raised to a power? Well, by this point, hopefully we know that it's to the negative first, right? 2 to the negative first equals 2 to 24,000k. So we have a base to a power, same base to a power, get rid of those bases. So we get -1 equals 24,000k, which means k is -1 over 24,000. That's our answer. All right, that's it for this video. If you have any questions, just let me know. Otherwise, have a great day.